let's talk about AI mastering games.
Mm.
For years, we watched computers conquer increasingly complex challenges.
Ah.
Checkers fell, then chess with Deep Blue. That was huge.
Absolutely. But there was always this one game looming. Go.
Go, yeah. It felt different, didn't it? Like this almost impossible summit for AI.
That's exactly right. It wasn't just like another board game. It was widely seen as maybe the ultimate grand challenge in that whole domain. The scale is just wow.
Staggering is the word. I mean, the numbers you shared from the source material, chess, maybe 35 moves per turn, games 80 moves deep.
Something like that, yeah.
Standard averages.
But Go, it averages, what, 250 legal moves?
250. And games easily hit 150 moves, sometimes more.
So the search space, the total number of possible games, it's just astronomically huge, mind-boggling.
Exactly. And trying to tackle that with, well, the traditional AI search methods.
Yeah.
That was the core difficulty.
Wasn't just the number of moves either, was it? It was judging the positions. Right. Go strategy is so much about potential influence territory. Things that are really hard to just slap a number on, unlike material in chess.
Which is why this paper we're using as our source today is, well, such a big deal. It lays out this completely new approach that finally cracked it.
Yeah, combining deep neural networks with sophisticated tree search.
And that system is the AI we're diving into today, AlphaGo.
AlphaGo.
So our mission here is to unpack the key ideas from this paper, figure out step by step how AlphaGo managed this breakthrough in Go,
Yeah.
and maybe explore why it mattered beyond just the game itself.
Sounds good. Let's get into it.
Okay, so we've touched on the scale problem. That massive search space, brute force search was just, well, impossible. The paper's very clear on that.
Oh, absolutely. You just cannot map out every possibility, even a few moves deep in Go. The number of options explodes way too fast.
And the tricks that worked for chess or checkers, like using value functions to estimate how good a position is, cutting the search short, why didn't that really fly for Go?
Well, those older methods often relied on humans' kind of handcrafting features, right? Like pawn structure in chess, you combine them, maybe linearly.
Right.
But Go positions are more holistic. Their value comes from these complex sort of nonlinear patterns across the whole board. Trying to build a value function for that, the old way, it just couldn't capture the strategic depth. Limited.
Okay, so evaluating positions was tough. What about narrowing down the moves to even consider? Reducing the breadth of the search.
So people tried things like Monte Carlo rollouts. You sort of randomly sample moves and play out quick games to get a rough idea.
Right, I remember that from backgammon AI.
Exactly. And in Go, especially within Monte Carlo Tree Search, or MCTS, this got programs to maybe a weak amateur level.
And MCTS was the foundation for the best Go programs before AlphaGo, wasn't it?
It was, yeah. But the paper points out they were still limited. Either the policies guiding the rollouts were too simple, too fast, or the value functions used were too basic, often linear, and couldn't really judge the complex positions accurately.
So they could explore, but maybe not always in the right places, and they didn't always know what they'd found.
Kind of, yeah. Their judgment, both for exploration and evaluation, was the bottleneck.
And this is where AlphaGo flips the script, right?
Yeah.
The paper talks about deep learning meets tree search.
Exactly. They brought in deep convolutional neural networks. These are amazing at processing grid-like data, like images.
So you treat the Go board, the 19 by 19 grid, like a picture.
Pretty much. And these networks are really good at learning complex spatial patterns directly from data without humans needing to define them explicitly.
So instead of programmers trying to code, this looks like good territory, the network just learns what good territory looks like from seeing millions of examples.
Precisely. And AlphaGo actually uses two key types of these networks.
Okay, first there's the policy network.
Right. The policy network looks at the board and basically suggests promising moves. It outputs probabilities for all the legal moves, which ones seem strong.
And the second one, the value network.
The value network looks at the same board position and tries to predict the overall outcome. Like, what's the probability the current player wins from here? It gives a score for the position itself.
And these two networks working together, that's how they tackled that massive search space.
Fundamentally, yes. The policy network narrows down which moves are worth exploring, effectively pruning the search tree.
Cutting out the less promising branches.
Exactly. And the value network gives a fast, much more accurate estimate of how good a position is deep in the search without needing to simulate all the way to the end of the game.
Okay, powerful tools. But how do they actually teach these networks? The paper describes this multi-stage training process that sounds really interesting.
It really is. It starts with supervised learning, stage one. They train what they call the SL policy network.
SL for supervised learning.
Correct. Trained on a huge database, 30 million moves from games played by high-level human experts. KGS 6 to 9 Dan players.
And the goal there was just copy the humans. Predict what a human expert would play.
Essentially, yes. Learn from the best human players. And it did pretty well. The paper mentions 57% accuracy in predicting the expert move on their test set.
How does that compare? Was that good at the time?
It was a big step up. The previous best the paper cited was around 44.4%.
Okay, a noticeable improvement.
Yeah, and what's really interesting, and they show this in Figure 2A in the paper, is that even small gains in predicting human moves led to surprisingly large jumps in the network's actual playing strength.
So it wasn't just memorizing, it was actually understanding something deeper.
It seems that way, yeah. It was capturing real strategic patterns. They also trained a faster, simpler policy at this stage, just for doing those quick rollouts during the MCTS simulations later. Speed was key there.
Okay, so stage one, learn to play like a human. But the goal is to beat the best humans, maybe find moves humans wouldn't. Is that stage two, reinforcement learning?
Exactly. They took the SL policy network, the one trained on human games, as a starting point. Then they refined it into the RL policy network.
RL, reinforcement learning.
Right, and they did this through self-play. The network played millions and millions of games against itself, against previous versions of itself.
Learning by doing, essentially.
Yeah.
Competing against its own best strategy.
Yes. The goal shifted. It wasn't predict the human move anymore. It was simply win the game, optimize for the final outcome. This allowed it to discover potentially new strategies, things not necessarily found in the human data.
And this RL policy, even on its own, without the big search component yet, how strong was it?
It was already very strong. The paper shows that just the RL policy network with no search won over 80% of games against the initial SL network.
Wow.
And it even beat Pachi, which was a strong MCTS program back then, 85% of the time, just the raw policy.
That's incredible. Shows how much knowledge was baked into that network.
Absolutely.
Okay, so a strong policy for suggesting moves, but you still need that accurate evaluation, right? Judging positions, that's stage three, the RL value network.
Correct. This network was trained specifically to predict the win probability from any given board state. And it used positions generated from games played by the strong RL policy network against itself.
So it's learning how valuable positions are based on outcomes from AlphaGo's own best play.
Exactly. Now, there was a potential pitfall here, a big one, overfitting.
How so?
Well, if you train the value network on lots of positions taken from the same game, all those positions are correlated, right? They all lead to the same final result, whoever won that specific game.
Ah, I see. The network might just learn to predict the outcome of that one game rather than learning a general sense of position value.
Precisely, like memorizing answers for one test instead of learning the subject.
So how do they get around that?
Their solution was quite clever. They created a massive new data set of 30 million positions. But crucially, each position was sampled from a different game of self-play.
Oh, okay. So each training example was independent.
Exactly. It broke that correlation and forced the network to generalize.
Nice. And was this value network effective?
Very. Figure 2B in the paper shows it was consistently more accurate at predicting outcomes than doing those fast Monte Carlo rollouts. And importantly, getting an evaluation from the value network was about 15,000 times faster than running a rollout simulation using the strong RL policy for comparable accuracy in its role.
15,000 times faster. That's huge for search efficiency.
Massive.
Okay, so now they have the pieces. A policy network for suggesting good moves, and a value network for fast, accurate evaluations. How do they actually combine these inside the Monte Carlo Tree Search?
Right, this is where it all comes together. The paper, and Figure 3 helps visualize this, shows how AlphaGo integrates these networks into its MCTS algorithm. It still has those four main phases you see in MCTS.
Selection, expansion, evaluation, backup.
Exactly. But the networks supercharge each step.
Okay, let's walk through it. How does selection change?
So when AlphaGo is deciding which existing branch of the search tree to explore deeper, it uses the standard MCTS idea of balancing exploration and exploitation. But the prior probability part, the initial guess of how good a move is, that comes directly from the SL policy network. Moves the policy network likes get a higher prior, nudging the search towards them.
So the policy network is constantly whispering, hey, check this move out, it looks promising.
Pretty much, yeah. Guiding the search intelligently. Then comes expansion. When the search hits a position it hasn't seen before, it adds it as a new node in the tree.
Okay.
And for this brand new node, the initial probability is assigned to all the possible moves from that position are again provided by the supervised learning SL policy network, the one trained on human data.
Interesting. They use the human trained one there.
Mm.
Okay, what about evaluation of these new nodes? This seems critical.
It is, and this is where they did something really neat. They evaluated the new leaf node in 2 ways at once.
2 ways.
Yep. First, they run the position through the value network to get that fast, learned prediction of the outcome. Second, they also run one of those fast Monte Carlo rollouts using the simpler, faster rollout policy all the way to the end of the game.
So, a sophisticated guess from the value network and a quick simulated game. Why both?
The paper suggests they capture different kinds of information. The value network gives a learned, perhaps more nuanced estimate. The rollout gives a concrete, though maybe noisy, sample of a possible future. They found that combining these 2 results actually worked best.
How did they combine them?
Just averaged them, basically.
Yeah.
A 50-50 mix, lambda equals 0.5, gave the strongest results in their tests.
Okay, makes sense. And the final step, backup.
Standard MCTS idea here. The result of that combined evaluation gets propagated back up the path the search took to reach that leaf node. It updates the statistics, visit counts, estimated values for all the nodes, and moves along that path.
So the tree gets smarter with every simulation, refining its understanding.
Exactly. Good lines of play get reinforced, bad ones get less attention over time.
And then, after all that searching, when AlphaGo actually has to pick its move for the game, how does it decide? Does it just pick the move with the highest calculated value?
Actually, no. It picks the move that was visited the most times during the entire search process.
The one it explored most often. Why do that?
The paper notes this was more robust, less sensitive to maybe one weird outlier evaluation deep in the tree. If the search keeps coming back to explore a particular move again and again, that's a strong signal. It's consistently looking like the best option.
Okay, that makes sense. This whole system, the search, the networks running constantly, sounds computationally intense.
Oh, hugely. The paper stresses they needed a really high-performance setup. Asynchronous, multi-threaded. They use CPUs for the search logic and managing the simulations, and powerful GPUs just for running the neural network calculations in parallel.
Right. The networks need the GPUs.
Uh-huh.
And they had different versions.
Yeah, they mention a single machine setup, like 48 CPUs and 8 GPUs. But for peak performance, they had a distributed version using something like 1,200 CPUs and 176 GPUs.
Wow. Serious hardware.
Definitely needed for this level of play.
So the big question, how did it actually perform? Let's start with other Go programs.
The results were dominant. In tournaments against the other top Go programs at the time, Crazy Stone, Zen, Pachi, all the known ones, the single machine AlphaGo achieved a 99.8% win rate.
99.8%. So basically unbeatable by any other AI then.
Pretty much. And they did experiments disabling parts of it, like using only the value network for evaluation or only the rollouts.
Yeah.
Even those simpler versions were better than the previous state-of-the-art programs. But the full system, the hybrid using both the value network and the rollouts, that lambda 0.5 mix, was significantly stronger. It won over 95% of the time against the versions using only one evaluation method.
So that combination really was key. The 2 evaluation methods were better together.
Definitely. And the distributed version, the big one, even stronger. It beat the single machine AlphaGo 77% of the time.
Okay, so it crushed other computers. Then came the real test, the one that made headlines, Fanhui, October 2015.
Yes. The match against Fanhui, the European Go champion, a professional 2-Dan player. This wasn't just a friendly game, it was a formal 5-game match.
The moment of truth, really. Could it beat a human pro?
And the result, AlphaGo won, 5-0.
5-0.
Yay.
A clean sweep against a professional Go player. The significance of that just feels huge.
It was enormous. This was the first time any computer program had beaten a human pro in full board Go without a handicap. And as the paper points out, most experts thought this milestone was, like, at least a decade away.
A decade. And AlphaGo did it years ahead of schedule. It didn't just meet expectations, it shattered them.
It fundamentally changed the landscape for AI in complex games.
People immediately compared it to Deep Blue beating Kasparov in chess. But the paper highlights some key differences, right?
Yes, very important differences. One big one is just the sheer number of positions evaluated. AlphaGo looked at thousands of times fewer positions per second than Deep Blue did.
Wait, fewer, even though Go is way more complex. How does that work?
It points to a difference in approach. Quality over quantity, maybe. AlphaGo wasn't just crunching possibilities through brute force depth, it was using its learned networks for more intelligent selection.
The policy network guiding the search.
Right. And more accurate evaluation.
The value network judging positions.
Exactly. So it could achieve incredible strength without needing to explore nearly as many raw positions. The paper sort of suggests this might be closer to how human experts play using intuition and pattern recognition to focus effort.
So less like a calculator meticulously checking everything, more like an expert using learned intuition to guide its analysis.
That's one way to think about it, yeah. And the other critical difference, how they got their smarts. Deep Blue relied heavily on a very complex evaluation function that was largely handcrafted by human chess experts.
People program chess knowledge into it.
Exactly. AlphaGo's networks, both policy and value, were trained primarily from data using general-purpose machine learning. Supervised learning from human games, reinforcement learning from self-play. It learned its own representations, its own evaluation function, its own strategies.
That feels like a really fundamental shift. From encoding human expertise to enabling systems to learn expertise themselves.
It really does. It showcased the power of deep learning and reinforcement learning for tackling these incredibly complex problems where human intuition alone might not be enough or is too hard to codify.
So wrapping up this deep dive, the core achievement here, based on this source, is AlphaGo solving Go this monumental challenge by cleverly combining deep learning with Monte Carlo Tree Search, reaching and frankly surpassing top human professional level.
Absolutely. Go was seen as this AI grand challenge, and its complexity, the huge search space, the tricky evaluations, mirrors problems in lots of other AI fields.
Yeah, we know from the past, like when MCTS itself became big in Go, those techniques often find applications elsewhere, right? Planning, logistics.
For sure. And this hybrid approach, this blend of sophisticated search guided by powerful, learned policy and value functions, seems like it has even broader potential. Learning directly from data or experience is key.
Which really leaves us with a final thought, something for you, the listener, to mull over. If this combination cracked Go, which seemed almost intractable for AI just years before, what other really complex decision-making domains out there, maybe in science, engineering, optimization, maybe even creative fields, could this powerful blend of learned intuition and intelligent search unlock next?